it's just a silly terminology issue, but some mathematician somewhere decided that a hyperplane is defined as n-1 dimensions. And so there you go. But yeah, in truth, the math is the same even if you have 0 to n dimensions. Therefore, flat is the more general term, and I guess is the one we should get used to. It feels to me like hyperplane is the term we all use, so I wanted that one to be the more general term. My intuition clashed with the established definition, and you can't fight the established definitions, so there you go. Well, you can, and I tried, and I lost that battle. Yeah, we can go around demanding hyperplane be defined according to our ways, but the mathematicians will win. They own their field. Point is, this is a flat. Okay, who cares what it's called? I don't care what it's called in this class. You can call it whatever you want. I have now educated. Moving on. Okay. Let us suppose we have a 2 flat here, because it's a 2-dimensional manifold embedded in, I don't know, 40-dimensional space.
You mean hyperplane?
God, leave me alone. Yeah, well, I've totally lost my train of thought now. How many times do we have to call f to compute this gradient of size 2?
How many dimensions there are?
I'm going to say that plus 1 because you need the starting point as well.
Okay.
So if there are 12 dimensions, you're going to have to call your function 13 times to compute this 12-dimensional gradient vector. Okay, what if we use this red approach? I'm sure there's a better name than red approach. What is it? Forward, backwards, central. Okay, it's called central differencing. Apparently you add half of h to it. You could just take an h that's half as big and it would be the same thing. Yeah, since h is arbitrary anyway. Okay, so if we're doing central differencing rather than finite forward finite differencing, how many times do you have to call your function in order to compute a 2-dimensional gradient? Isn't it 4 times? I think it's 4 because you have to do plus and minus h in the x1 direction, and you have to do plus and minus h in the x2 direction, and then you have to compute the y's and then divide by the h's to get the actual gradients in all those directions. Okay. The point is, you can compute gradients empirically, and you should be able to do that. This is not how we're going to do it in this assignment, but in fact, it would be a really good thing for you to do it this way and compare it with the results you get using backpropagation. That will confirm that it is actually computing the gradient correctly and you understand what is going on. There's another way to compute gradients, and that with a neural network, and that's called backpropagation. So backpropagation. And what backpropagation does is it's an algorithm that we apply to a neural network, and it returns to you the gradient. And you might say, well, that's great, but we already have finite differencing, which works with arbitrary functions, so why do we need a specialized algorithm that works with neural networks? And here's the reason. Your neural network is going to be big, and by big I mean they have a lot of parameters. Neural networks on average will have 1 million parameters-ish. I don't know if that's a good average, it depends what you're averaging over. But let's say there's 1 million parameters in a neural network, and you want to compute the gradient. How many times do you have to call your neural network to do it? Well, you have to go forward 1 million times and backward 1 million times. Well, no, just forward 1 million times. And then you've got the derivative with respect to each of the 1 million parameters in the neural network. If you want to compute the derivative for all 1 million parameters using backpropagation, you call backpropagation 1 time. It goes forward across your network, backwards across your network, and then you know the gradients of all 1 million parameters. See how that's a lot more efficient?
Wait, which one is more efficient again?
Backpropagation is more efficient. So in fact, if you have 1 million weights in your neural network, it's approximately 500,000 times more efficient. Because in one pass, it computes for you the gradients of every single weight in your neural network. You can train a neural network by finite differencing, but nobody does, because why be a million times slower, right? Not for this class. I'm going to say if you know how to call back propagation and it returns to you a number and you know that number is the gradient, I'm content with that. But to make sure you did it right, I strongly recommend you write a little unit test that does this central, use finite differencing, use the central form of it rather than the forward form of it, because you get more accuracy that way. So use central finite differencing. Is it called central differencing or central finite differencing?
It doesn't matter.
The central difference. Okay. Or it doesn't matter.
Yeah.
I'm giving you code. The code has backpropagation already implemented. You're just going to call it. It's going to give you some numbers. And then you're going to do central difference. You're going to compute the central difference, and you're going to look at them and say, wait a minute, this one's twice as big as that one. And then you'll realize, that's because it's just off by a factor of 2 because somebody absorbed a constant in the math somewhere. But as long as they're always proportional by exactly the same amount, then you'll say to yourself, yay, this is actually computing the derivative and I know what's going on. Okay. The other thing I want to point out is a neural network is a function of two things. It's kind of like this. Y is equal to f of x comma w, where w is the set of weights in the neural network and x is the inputs to the neural network. In fact, I guess you could say any function has both inputs and parameters, right? Usually, when we use backpropagation, we're differentiating with respect to the weights. But the Jacobian is differentiating with respect to the inputs. And that's a significant difference that you need to understand. Makes absolutely no difference at all, because inputs and parameters of a function are really the same darn thing. It turns out backpropagation computes either. You can do forward differencing or finite differencing or central differencing, whatever it's called, to compute either. You just have to make sure you know what you're doing. Okay, so let me point at the code now and show how that's done. Let's see, what do we call it? Kalman CPP, source, neuralnet.h, I believe. Okay, this is the header file for the C++ version of my neural net class that I supplied for this Kalman filter assignment. And is the same thing as the one you used in the last assignment you did a neural net with, the Q-learning one. So you're already somewhat familiar with this. Right, somewhere. There we go. Backprop. Okay. I should have stated in the comment here, the backprop function assumes you have recently called the forward prop function. So don't just try to call backprop. It won't give you anything you want. Call forward prop first. Then you have to call compute output layer blame terms, and then you can call backprop. So you need to call all three of these functions. Okay? The forward prop call is kind of like the first time when you compute the initial starting spot. Does that make sense? You're saying, this is where I am, because you have to tell it where are you at, and you have to run through your network to compute the output. So you need both the inputs and the outputs at some point. And that's what the forward prop step does, yes. Yes. We do not need labels, we need only in. In this case, in is the x vector. So this is the vector of x1 and x2. All the places where you are at in your space, it's this red point that specifies where on the neural network you want to differentiate.
I thought you implemented the way that you need to find error signal first.
No, so most implementations of neural networks just give you one function that's called train, and you pass the input and the corresponding output, and it computes the error signal, and it does all the stuff for you. I've kind of broken it up into a bunch of smaller functions so we can use it to do more useful stuff. So in this case, you are going to want to call these three functions in order, starting with forward prop, and to this you pass only the input. And you pass the input to basically say where you're at in the space. And internally, it will compute some predicted output. In fact, I think it returns it to you, doesn't it? Yeah, it does. It does return it to you, but you're not really going to need it, so you can just ignore what it returns if you like. Sorry, what's that?
What is the range?
Okay. After you do a forward pass, then we need to tell it how bad it has done. This is the error signal.
Oh, okay.
So usually what you do is you provide a target value. So I fed as my inputs, I am right here where that x is, and it computed the height, the verticalness of that point on the manifold, right? Now if I said to it, well, yes, you computed right there, but I actually wanted you to be up here, then the difference from here to there is the error. And so what this function does is it says, okay, you've already done your forward prop and computed your current prediction. What did you want me to predict? And this function is just a simple subtraction. It just subtracts target minus prediction and puts blame on the output units. So it tells the output units, this is how wrong you were. So the way the error term works is it's the first derivative of the error signal. So in fact, computing the simple difference here and blaming the outputs based on the simple difference is the same as minimizing over the squared error. So we are minimizing the squared error, and we do that by blaming it according to only the difference in error. Is that sufficiently clear?
So where you pass the targets?
That's, you mean, let me restate your question. In the Kalman filter assignment, what do you pass as the target? Is that what you're saying? Or are you asking in general?
Okay, I'm just saying, if I take a neural network
Uh-huh.
and I want it to approximate some function,
Yes.
f of x, and it's got some weights that we tune, and it now fits our function, and now I want to differentiate that function and figure out what the derivative is.
Yes.
At point, some point x.
Yes.
So I call forward prop at x, and I call the compute blame of the output layer at where? Why?
That question right there is the whole point of this lecture. That's what I want to get across to you. So thank you for nailing the question. And I need to not answer that question so that you'll really get it.
Okay.
But I'm gonna try and talk all around it, and hopefully it'll sink in the next few minutes. Yeah.
Can you repeat the question?
Yes. The question is, what do we use for target when we compute the output blame terms? In other words, there's 3 steps to this neural network. Forward propagate, assign the error, and then back propagate. And what back propagate does is it says, okay, well, this is how wrong the output units were, and based on that, we're going to derive how much blame the hidden units deserve, and how much blame their callers deserve, and how much blame their callers deserve. And we basically go backwards pointing the finger. I only did it because he said blah, blah, blah. Well, I only did it because he said blah, blah, blah. And well, I did that because he said that. And then in the end, all the units in the network have blamed each other, and then they all repent and correct their ways. And next time we feed in these values, we compute something a little closer to the target.
Yeah, but we're not talking about training or updating the weights at all.
Exactly. In this case, there is no target because we're not trying to change the neural network, and we're not ever going to update the weights. We're only trying to compute the error with respect to the inputs. In other words, we're trying to do this, we're trying to compute that, right? We want to do something very much like finite differencing. So how do we do that? And the how do you do that comes out when you realize that backprop really is just computing the derivative. That's all it is. It is the derivative. And when we do gradient descent, the reason we do backprop is because the blaming of all the nodes in your units, all the nodes in your network, is computing the gradient so we can step in that gradient direction to update the weights. We're not going to step in the gradient direction. We're just doing it now so we can compute the Jacobian, so we can do Kalman filtering.